Okay, so this is another image of radioactive decay, and this is specifically the carbon-14 isotope. So you can see that we have carbon-14 starting out on the left. We go through some amount of time, and that carbon-14 goes through decay, expels a beta particle, turns into nitrogen-14 plus an electron and plus an antineutrino. If you look at the table underneath this figure, you'll see a list of several parent isotopes and daughter products. The key point of this is the amount of time that represents one half-life. So in carbon-14's case, we have a very short half-life with respect to how old we believe the Earth is, only 5,730 years. That amount of time would not be good for measuring a very long time because, as you can imagine, the amount of carbon-14 that would be present would be next to nothing. So what we need is a half-life that is similar to the amount of time that the Earth has been present. It turns out that uranium-238 decays to lead-206, half of it every 4.5 billion years, which is convenient, seeing as the Earth has been determined to be 4.6 billion years old. So when choosing your parent isotope that you would like to measure the daughter isotope of to determine the date, the age of whatever it is that you're aging, make sure that your half-life is something that's close enough to your expected age to make the ratios measurable. Otherwise, as you can imagine, if we used rubidium to strontium at 48.8 billion years, or any of these longer ones, we would still not be able to have enough daughter material to make the ratio very measurable. So that is why we don't use carbon-14 for every type of dating